is to be able to get this expression. So this expression is that's B transpose dV. So our target here is to be able to just get this expression. Whatever this value is, we don't really care at the moment. We just wanted this one here. Okay, that's what we wanted to get out from this principle of virtual displacement. Take note, we were able to derive it using the method of weighted residual, wherein the weight is the shape function for the Galerkin method. So, we are only focused on that elastic region. And then I have this one to be corresponding to my force, stress, force, E, and displacement. Yes? So that your strain energy SE is equal to the area under this elastic curve. Your elastic strain energy is that area under this elastic curve, which is 1/2 multiplied by stress strain. But actually you integrate this one, so that's the volume integral of that stress strain dV. 1/2, sorry, because it's a triangle. So it's 1/2 the stress and the strain. So that is your stress, that is your strain. So this is now the area under your elastic strain diagram, or elastic stress strain diagram. Alternatively, you can also have this one to be, say that will be equal to the force multiplied by the distance, 1/2 the force multiplied by that distance, but the displacement. Okay? So we can now equate this one here, 1/2 the volume integral of this one, dV, equal to 1/2 that force multiplied by that displacement if you apply a force. So we can have this one to be F multiplied by that displacement minus that strain energy equal to 0. So that's the first step here. If you have a multi-degree of freedom, this one becomes a vector and this one also becomes a vector. Right? This one is just for so-called one-dimensional. If you have a multi-degree of freedom system, then this one becomes two vectors. So to write this one here, so for multi-degree of freedom system, so you have this one to be a vector. So I'm just going there to put I there for the nodes, because you have lots of nodes there. And this is to be multiplied by your displacement. And then the same, no change here. Volume integral of your stress strain dV equal to 0. So this will be your general equation. That's a 9. So if you can recall, for our finite element, we use lots of these I's to denote that there are different nodes in a system. Yes, so what's next? We move on now to discuss this virtual displacement. So please accept whatever I say at the moment. So you can challenge me later after reading your notes. I welcome discussions. So what happens here for virtual displacement is that we have this system here, and then we assume that the stress is the same, and then apply a small, let me exaggerate, displacement. So that you will have, so if I'm going to write it here, and just copy this part here, you will have that virtual displacement. That virtual displacement maintaining the stress and just applying a very small, so I'm just exaggerating here, a very small displacement. So I'm just exaggerating for us to see, and this will be your U virtual and maintaining the same stress as your previous value here. Okay, so that's the concept of a virtual displacement. Just very small, very infinitesimal displacement, virtual, meaning it's not real really. So you just assume that you will have a similar stress applied to that, and then you will have this one here. So again, the concept here is just taking another virtual one. Okay, so in the meantime, just please accept whatever we have it here, and then we have now your work done to be equal to the force multiplied by that displacement. So what's next with this one? So once we understand this concept here, the next thing we're going to do is to consider that your work done, virtual, is equal to force multiplied by a distance. In this case, our force will be your displacement. So this will be a force. Okay, so I'm just going to put there, if you have a multi-dimensional system, you have a force I, the same. So this is transpose. And then this is to be multiplied with, so U and another U there. This will be multiplied by your virtual displacement. So we have a virtual work done. Work done is equal to the force multiplied by a distance, but in our case, force multiplied by that displacement. So your work done is equal to the force multiplied by your virtual displacement. So virtual. So anything virtual will be affected by that virtual displacement. Yes? So your virtual work done, if you go back here, is equal to your virtual strain energy. Force distance equal to strain energy. So we're using the same concept now. Work done equal to virtual strain energy. And what is your virtual strain energy? The volume integral of that stress multiplied by the virtual strain dV. So this one is the same. Transpose, and then you have this one to be your virtual. Okay, so they are equal. Yes? So as you can see, they are actually the same. It's just that for this one and this one, for virtual displacement, you only have this displacement as well as the strain to be virtual. Okay? So work done is equal to the strain energy. What is the work done? That will be your force multiplied by the displacement. What is your strain energy? That will be the area under this one here. which is the volume integral of the stress multiplied by that strain. And that strain is a function of the virtual displacement, so you have here a virtual strain. Okay, so please bear with me for this one. Again, all are the same, it's just that for displacement strain you put in a virtual assumption. So please bear with me with this one here. So the next thing that we're going to do here, okay, so once we have this analogy now, yes? So once we have that, let me just continue here. Let me just write this one here. Okay. So strain is virtual, displacement is virtual. If you have your displacement as virtual, let's have a look at our strain. So your strain is equal to du dx, yes? And previously we have this, if we introduce a shape function, this one will be dx of that n, yes, multiplied by your ui. So we can take out this one now, so this will be the n dx ui. This will be, checkmate, here if I'm wrong here, whether there's a transpose there, that will be b, dn dx is b, so you have ui. So this will be your strain. So anything that has to do with virtual, you will have a v here and a v there. But take note, your virtual displacement is just another identity matrix. Okay? Your virtual displacement is just an identity matrix, very simple. So I can, if I want to have my virtual strain, that is also b, ui, v. So, good? Okay. Now, I want to go to this one here, f, the same, I'm just trying to put in the values here. I'm going back to that virtual analogy there, ui virtual, this now is equal to minus the volume integral of your stress virtual strain dv equal to 0. What is the equation for your virtual, what is the equation for stress? So this is not virtual. So what is the equation for your stress? Your stress is equal to your modulus multiplied by your strain. So we want to bring it here. So once you bring it there, what happens? So you have now Fi virtual minus the volume integral stress, strain, virtual strain, dV equal to 0. Please have a look. So no change. It's just that this one, we have this one here, we have that, this, and so on. Oh, sorry, E. Okay? Modulus. So what's next? We can now put in our this one here. We have this one is virtual, that is E, that is E. Okay? I can now, sorry, did we have this one to be, can you check me whether this one is a transpose? I think this one is a transpose. It is transpose. So I'm just going to rewrite that here. So we will have the this one is the B transpose. I'll just put it here. U I. So just an example. If you have this one to be, is it B transpose? Okay, so this is your B transpose. And then I'll have your virtual strain be B transpose. I'm going to take the, let's take this one as another vector. This one is your virtual. I'll take that as another vector. Okay? So let's try to substitute everything here. So I have now my Fi transpose Ui virtual minus, or let me just bring it to the other side, volume integral. Let me bring out that E first. Your strain here will be B transpose UI. This is not virtual. Yes. And then I'm going to put in the virtual B transpose your virtual displacement, and then that is now dV. Yes? So this will be your strain. This will be your virtual strain. Okay? So just let me show you, your strain is equal to, say, B1, B2. So if we have B transpose, say UI, just an example. So this one will be B1, B2. And then you have U1, U2. So this will be equal to B1, U1 plus B2, U2. Okay? So I think we got this one before. So you have dN1 dx U1 plus dN2 dx U2. So we got this equation before. So this is just trying to expand on this one here. So you can do the same with that virtual displacement. Okay? So what's next? So the next thing that you're going to do here, so take note of this one. Yes, this one is the one, a scalar value. So just take note of that. So it's a scalar value, it's not a matrix. So it's a scalar value. So if that's a scalar value, this is a scalar value. Let's try to work on your virtual displacement. So your virtual displacement is just a simple identity matrix. Depending on the number of degree of freedom, that will be the size of your identity matrix. So for 2 degree of freedom system, then our virtual displacement is a 2 by 2 identity matrix. So say for example, in our example, we're just looking at the bar system, wherein we have 2 degree of freedom per element for bar. So we have the 2 degree of freedom per element. Your virtual displacement is a 2 by 2 identity matrix, or simply 1, 1, 0, 0. Okay? So this one is virtual, that is virtual. I would like to continue. This is okay. So